All right, let's just jump right in. The transistor. It is, without a doubt, the bedrock of our entire digital world. It's the most manufactured object in human history, period. We're taught to think of it as, a simple switch or an amplifier. But what if the story we all learned about how it works is leaving out the most important piece of the puzzle?
Right? We learn that a tiny little current at a pin called the base magically controls a huge current flowing through another part called the collector. It's simple, it makes sense, it's easy to work with. But is that what's actually happening on a physical level? In this explainer, we're going to pull back the curtain and uncover what's really going on under the hood.
So, to get to the bottom of this mystery, we first need to get a handle on the two fundamental ways that charges can move through a semiconductor. We're talking about our familiar electrons, of course, and their little buddies, holes, which you can just think of them as the absence of an electron, acting like a positive charge.
Okay, first up is drift current. This is the one we're all pretty familiar with. You apply an electric field, a voltage, and it shoves or pulls the charges along. It's kind of like a river, where gravity is forcing all the water to flow in one specific direction. Simple enough. But here's where your intuition might get a little scrambled. The actual speed of this drift is shockingly slow. In a normal copper wire with current flowing, a single electron is just moseying along at about 23 micrometers per second. I mean, a snail is faster than that. It's wild, right? The signal travels at nearly the speed of light, but the electrons themselves are just crawling.
Now, the second way, and this one is super important for our story, is diffusion current. This happens all by itself, without any electric field at all. It's just the natural tendency for things to spread out. If you have a whole bunch of particles crowded together, their own random thermal jiggling is going to make them spread out into the less crowded areas. The classic example is a drop of ink just naturally spreading out in a glass of water. That's diffusion.
Okay, so we've got drift and we've got diffusion. Now let's see what happens when we put these two forces together to build the absolute heart of a transistor, the p-n junction. This is where the real magic starts. So you take a p-type semiconductor, which has a ton of those positive holes, and you stick it right next to an n-type, which is packed with negative electrons. The instant they touch, diffusion kicks in. Electrons from the crowded n side spill over to the p side, and holes from the p side spill over to the n side. And right where they meet, they cancel each other out, leaving a little zone that's been depleted of any free charges. And this is the brilliant part. Those uncovered ions that are left behind, well, they create their own little internal electric field. This field acts like a barrier, a potential barrier. You can think of it like a hill that the charges now have to climb to get across. This hill pushes back against any more diffusion, and the whole system settles into a nice, stable equilibrium. For most of the charges, getting over that hill is just too hard. But, and this is the absolute key, for the minority carriers, things are totally different. We're talking about the few electrons hanging out on the p side, or the few holes on the n side. For them, that barrier isn't a hill they have to climb up. It's a waterfall. They fall down. If one of them just happens to wander to the edge, whoosh, it gets swept across instantly. The only thing limiting that flow is how many can get to the edge of the waterfall. You gotta remember this waterfall analogy, it is crucial. All right, now we have all the pieces we need to finally tackle the transistor itself. So let's start with the common story, the one you'll find in pretty much any introductory textbook.
A bipolar junction transistor, or BJT, is really just two of those p-n junctions we just talked about, slapped back to back. In an NPN type, you have this super thin, lightly doped p-type material, the base, sandwiched between a heavily doped n-type emitter and a moderately doped n-type collector. And all these details, heavy doping, thin base, they're all engineered for a very specific reason.
So the story goes a little something like this. You inject a tiny little current into the base, and that base current acts like a control knob, opening a valve that lets a much larger current flow from the emitter through to the collector. Simple cause and effect, right?
In this model, the base current, that little IB, is supposedly caused by a few electrons that get lost on their way from the emitter and combine with holes in the base. The rest of the electrons make it across and become the collector current. The gain, which we call beta, is just the ratio between the current that makes it and the current that gets lost. It seems to make sense, but
is it what's physically happening? This is where we have to peel back a layer and look at a deeper truth. It turns out there's another way to look at this whole thing. It's really a tale of two different models.
So here's the question that kind of breaks the simple story. What physical force, What mechanism allows a handful of electrons bumping into holes in the base to magically command a torrent of millions of other electrons to flow into the collector? The current control model, it doesn't really have a good answer for that. It's more of an observation of what happens, not an explanation of why.
And this leads us to the heart of the debate. Is the transistor a current amplifier, where the base current causes the collector current, or is it what's called a transconductance device, which is just a fancy way of saying its output current is controlled by an input voltage, where the voltage between the base and emitter, VBE, is the real puppet master?
Well, this quote from the source material just lays it all out on the table. It says the base current is actually just an unwanted leakage. It's a side effect, not the cause. It says base current does not control the collector current. Only the base emitter voltage, VBE, controls the collector current. Wow.
So, if voltage is the real king here, how does it all actually work? Let's put all the pieces we've learned together.
The secret, it turns out, is that electric field. Remember that potential barrier, the hill at the PN junction? Applying that forward voltage, VB, doesn't push current. What it does is it lowers the height of the hill.
So here's the real chain of events. 1, you apply V-bias, and the hill gets smaller. 2, now that the hill is smaller, a massive flood of electrons can easily diffuse across from the emitter into the base. 3, because that base is so incredibly thin, most of those electrons very quickly wander over to the edge of that base collector waterfall and get swept down into the collector. That's your collector current. And that tiny base current, that's just the few unlucky electrons that happen to bump into a hole and recombine before they can make it to the waterfall. It's a consequence, a side effect, not the cause.
And what's so amazing is that this isn't just some weird transistor trick. This principle of mobile charges rushing in to shield fixed charges and changing an electric field is totally universal. It's the same fundamental physics that happens in ionic solutions in chemistry and even in the ion channels that make our own brain and nervous system work. It's everywhere.
So if the current control model is just a convenience story, should we just throw it out? Is it useless? Well, no, not at all. It's all about using the right tool for the right job.
This table really sums it all up. The current control model, using that beta value, is a fantastic abstraction. For day-to-day circuit design, it's simple, it's quick, and it works great. But if you really want to understand the deep physics of what's going on, or why a transistor's behavior changes so much with temperature, you absolutely need the voltage control model. One is the tool for the circuit designer trying to get a job done. The other is the tool for the physicist trying to understand reality.
So we've seen that a really simple, useful story can sometimes mask a much more complex and, frankly, a much more elegant physical reality. It really makes you wonder, doesn't it? What other simple models we use every day, those for dummies explanations, are just the tip of the iceberg, hiding a much deeper and more fascinating story underneath.